Hey guys, we're going to do page 6. So it says, use geometric descriptions of rigid motion to transform figures and to predict the effect of a given rigid motion on a given figure, a given two figures, and use definitions of congruence in terms of rigid motion to decide if they're congruent. So first off, I want to define rigid motion. That means angles stay the same and side lengths are the same. So this is the concept of rigid. It doesn't get any bigger or smaller. What transformation maps the solid figure on the dotted line? It looks here like this would be a perpendicular bisector. Each line, when we connect them, there is a line that is a perpendicular bisector. So this looks like it's reflected over a vertical line. Cool. Question number 2. Select all the rigid motions. Ooh, select all. So we've kind of been preparing for that to get from the preimage. So, oh, there's an announcement. This is before, and this is after. So, notice we've been practicing this. This is pointing. If we think of this as a pointer, now it's pointing that way. So it can't be transformation. Could it be a 180-degree rotation? Rotate 180. So if this was a clock, 12, and that's 3, and that's 6, and that's 9, 290s, so now this thing would be pointed up and then rotated again. It's pointed to 3 o'clock. I like it. So I'm going to pick yes. What about a glide reflection? So glide reflection would be scoot it over here, right? Glide, that's this concept of glide. So if I scooted it over, it would now be here. And then if I flipped it over, I'm still not getting it happen. If I flipped it over, it would now be upside down. I kind of think of this as like a dog. You see that? If I flipped it upside down, now the dog is upside down. But it's still going to be pointed this way. So let's see if I could draw that. If I flip it upside down, now the dog is upside down, but pointed the wrong way. So I'm not going to pick that one. No. Pointed wrong way. All right. What about C? So let me start over and try that. C says rotating 90. Okay, so if we rotated 90, either you're going to be pointed, right now you're pointed, its nose is pointed 9. So if you rotate 90 counterclockwise, you'll be nose pointed down at the 6, or clockwise pointed up at the 12. And then reflect across a vertical line. So let's see if a vertical line. So if I rotate this 90, the dog's nose would then be pointed up. Right? Or it would be pointed down. And then if I reflect it over a vertical line, it's still going to be pointed up. This one's still going to be pointed down. So that, I'm not getting this. No. So I'm going to say no. Pointed up or down, not right. I need it pointed right. What about a reflection across? So let's start over again. What would happen a reflection across a horizontal line and then a rotate 90? So if I reflected it across a horizontal line, that's flipping it over. So let's see. So its nose would still be pointed, but it would just be the upside down dog, right? Reflect across a horizontal line. Rotate at 90, it would be pointed up or down. Same thing. No, it would be pointed up or down, not right. E, it says reflect across a vertical line. All right. That's nice. So a vertical line, it would now be pointed this direction, right? I like it pointed right, then reflected across a horizontal line. Ooh, I like this. So let me get it all the way over here. If I reflected it across a vertical line, here it would be, and then flip it over, it would land on top of there. It's definitely pointed right, so we're going to say yes. So there's our answer, A and E. Question number 3. Which triangle is congruent to PQR? PQR. Okay, we use Pythagoras, so we're going to get Pythagoras on board. We're going to use the Pythagorean theorem, which is a squared plus b squared is c squared. But you don't really, you kind of just can use part of that. So there is an invisible right triangle, and we're just going to make those come into vision, right? Here's this invisible right triangle. Notice that RQ has to be the hypotenuse of a 1/3 triangle. So that's the hypotenuse of a 1/3 triangle. So if there's a twin on this page, it also would have a 1/3 triangle. See this one? Let's see if we can find another one. This one, a 1/3 triangle, okay? So RQ is equal to the length, 1 squared plus 3 squared, and take the square root. You also know this would have to be the same length, and this would have to be the same length as that length. So we're going to prove that somebody, or more than somebody, is congruent to PQR by side triangle congruence, because they have all 3 sides equal length. All right, now let's investigate the next length. I see a triangle here, PQ, is a 2/3 right triangle. So this length, PQ, has to equal the square root of 2 squared plus 3 squared, whatever that number is. You don't even really need to find it, because you're just going to find one that matches it. So this one, that hypotenuse, is equal to the length 2 squared plus 3 squared. This one, excuse me, would also be equal to the length 2 squared plus 3 squared, right? No, that one doesn't have any one. No. Ooh, okay. So we've now eliminated this one because it doesn't have a length 2 squared plus 3 squared, and we've eliminated this one that also does not have a length 2 squared plus 3 squared. Interesting, right? So now we can finish this out with our last side. This has a length that's 1/2, the hypotenuse of a 1/2. So that length, which is the length of PR, has to be equal to 1 squared plus 2 squared, and take the square root. And there we have it. There's the 1/2 and take the square root. So they have all 3 lengths equal. So PQ is congruent to, it's a 2/3, right? PQ is congruent to DE, and RQ, which was that 3/1, is congruent to EF, right? And our last one, PR, is that 1/2 right triangle. That would be DF. So notice we have all 3 sides are congruent. So we can say that, now let's label them in the right order. So PQR is labeled PQR. I went across the longest side and the medium, but not across the smallest side to name it, PQR. So we're going to do the same thing here. we're going to go across the longest side and then the medium side to name it. So we have to name this DEF. DEF. It says which triangle is congruent, check, and it said state which pair's sides are congruent. Check, check, check. Question number 4. The vertices of a triangle JKL have these coordinates. Under which transformation is the image not congruent? So by translating 2 units to the right and 2 down, translation is rigid motion. So we're going to say yes. Let's keep reading. Oh, because I'm picking which one is not congruent. So this is rigid motion. So that's yes, congruent, but we're looking for which one is not congruent. A counterclockwise rotation around the origin. That is rigid motion. So that is a yes, congruent. A reflection over an axis. Reflection is also rigid motion. And so we're going to say, yes, that would make them congruent. So the last one, and this is the word we're looking for, a dilation makes things larger or smaller. So that's the one that is not rigid motion, which means that's the one that's not congruent. It would be similar, but not congruent. So we're reminded, this is like the mommy and the baby. If I have a triangle and I blow it up, these are not congruent. They're not equal in measurement. Their angles are equal and their sides make the same ratio, but they are not congruent and it is not rigid motion. So we found our answer D. Okay, question number 5. What transformation would produce congruent figures? Okay, so this is that is translation, and translation is rigid motion. And so we're not going to pick that one, right? Because that would produce congruence. If you took it and blew it up twice as big, that's dilation. Yep, this y coordinate's being blown up twice as big. And this one, both the x and the y. So which one would produce a congruent? Absolutely, we pick A. This one is congruent. So whatever the shape is, we don't know what it is. We're going to move it 4 to the right and 3 down. So whatever the shape is, it's going to move 4 to the right and 3 down. So this will be the new location. This shape doesn't get any bigger or smaller. That's why we would call that a congruent transformation. Question number 6 says, a figure undergoes translation, reflection, and dilation. Will the image be similar? Why or why not? So translation, reflection, and dilation. So the answer is yes to all. So let's focus in on D. When I translate, we just said, it would be similar, even though it's the same size. It's congruent, yes, but it's also similar. So to be similar, let's write it down. Similar means angles are the same and the sides are the same ratio. So although that seems weird, if this is a 3, 4, 5 triangle and we scooted it over, it's still a 3, 4, 5 triangle. Maybe we spun it a little bit. Notice the sides, we could make a ratio. The small side, 3. The medium, 4. The large side, 5. And this one also has a side 3, 4, and 5. Their sides make the same ratio. They just happen to make the ratio of 1, right? So let's read. Then we also already know that by translating and reflecting, those are definitely going to create this similar. Dilating creates this, where the shape is blown up or shrunk. So, no, dilation is not rigid motion, so the image is not similar. No good. Yes, any number of rigid motions and dilations will always produce an image similar. No, I like that. Let's keep reading. No, when more than one transformation is applied, the image is not similar. That's not true, and we know it. So why would that not be true, though? If this one got scooted over here, and now here it is, and then blown up, notice that's similar. So a combination actually creates similar shapes. Last one, yes, since only 3 were applied. So yeah, so there's no rule that like you can only do 3 or only do 2. Any combination would work. So we're going to pick B. Any combination of any of these would create similar triangles. Thanks for joining us. Check out the next video for